Recording started. Now let's share the screen. All right, good afternoon, everybody. Last time we stopped here on the transformer connection. So again, we are still in the transmission overview transmission file. So let's talk a little bit about the connection of the transmission. Basically, we can say we can connect the transformer, any three-phase transformer into three connections, which they can be Y to Y, delta to delta, Y to delta, and delta to Y. Then the thing that we need to know, which is basically how to distinguish this connection is a delta and if this connection is a Y. So basically, look, when Y connection can be like this. There's something here of phase A, phase B, phase C. This is for the live and the neutral. All of them are connected together. So here is A, B, C, and the other one is the neutral. This is how we connect Y side. And how about delta? To connect delta side, basically, we can have, like, for example, this one. So the leaving of the first one will go to the second one, the first wire of the second. It will go out, then go there, then the same thing here. Then here is phase A, here is phase B, here is phase C. This is how we connect delta as well. So when you look at it, that's the overall thing. Then in order to connect Y and delta, there are like the ways how we can connect the three-phase transformer. Like for example, this is Y to Y. So you can see here is the neutral, while the phases are over there, like here. Then to connect Y the other side, the same thing. While, however, in delta, you will see the negative of the phase A will go to the positive phase B, and the negative here go here, and this one will go here. So all of them will be in delta shape. Then, however, the other phases, phase A will enter here, phase B will go here, phase C will go here, and so on. Then the other thing about the construction of Y delta transformer. So when we have Y delta, the first parts, which is, for example, like Y delta and delta Y, like for example, like delta Y, you will see this is a delta shape. This is in delta, while the other side is Y. Here's the neutral of the other side, and so on. But keep in mind, when there is Y delta or delta Y, there must be a phase shifts 30 degrees or multiple of 30 degrees. So when we have Y delta or delta Y phase shifts, there must be a phase shift with plus or minus n times 30, multiple of 30s. So it can be 30 degrees or negative 30 degrees, or for example, like 150 degrees, negative 150 degrees, and so on. So just like a multiple of 30s. So there must be a phase shift when we have Y delta and delta Y. While when we are talking about delta delta Y Y, there is no phase shifts. No in both cases. While if we are doing delta to Y or Y to delta, there must be a phase shift. The three-phase system here, the overall, like we'll see this is in Y shape or star shape. Then this is in Y as well. So when we are dealing with Y to Y, so the overall given voltage every time in line to line. So the given voltage is always line to line. Therefore, in order to find line to neutral, which will be line to line divided by root of 3. Then the other thing, since we have the turns ratio n equals n2 over n1, then basically we have I would say V primary divided by V secondary equals N1 divided by N2. Therefore, V secondary will be V primary times N1 over N2. Then we can say donates N as N2 divided by N1, which yields to V primary divided by N. That's how for the V secondary. Then how to calculate V secondary? V secondary line to neutral equals V secondary line to line divided by root of 3. Therefore, we can say the same thing for V primary as well. Line to neutral equal V primary line to line divided by root of 3. Then as a result, to find V secondary line to neutral, which will be V primary line to line divided by square root of 3 times N. That's how we get this value here. Then if we are talking about V secondary line to line, it will be V primary line to line divided by N. There is no root of 3, and that's how we get this one. Then the same thing can be applied when we are dealing with delta and y. This is for y to y. While when we are talking about delta to delta, there is no neutral. Then the voltage is line to line always. And is always. So no V line to neutral. Then we can say V primary line to line equals V secondary line to line divided by N. And that's it. Let's go to the next one. Here, delta to y transformer. In the y side, or y to delta, in the y side, there is line to neutral. In the delta side, no line to neutral. Everything is only line to line. So the thing here will be to find V line to line, V line to neutral, which will be V line to line divided by square root of 3. This is the secondary. This is the primary. The secondary, which is V line to line divided by, or I would say like the primary, the secondary, which is the same as line to line in the secondary. So in other words, it's which will be V line to line divided by square root of 3 divided by N. Or in other words, let me do it again, which is this one is V primary divided by N. Then which is V line to line divided by square root of 3 divided by N, which is V line to line divided by root of 3 times N. And keep in mind, there must be phase shifts and phase shifts. What's the value of phase shifts? Again, it's plus minus N times 30, what's the value of N? It can be 1 or 3 or negative 1 and negative 3, whatever. So how can we define it? We will talk about it next chapter in the transformer. We will talk in deep details about it next lecture. Which one, how to identify, or I mean, I would say like next, I would say next week, to identify how to identify the values of the angle. And the same thing here for the line to line. So here, V primary is V line to line. So V secondary equal V primary divided by N, then which will be V line to line divided by N. Then in order to calculate V secondary, again, V secondary, this is line to neutral. V secondary line to line equal time square root of 3 times V line to neutral. Secondary, then it will be square root of 3 times V line to line divided by N. And that's how we can find it. Okay? Let's look at this example. Assume we have a 3-phase transformer with the nameplates given as 20 megavolt ampere, and we have 345 Y to Y. So this is a step-up transformer. And with the leakage reactance 12%. So the transformer connections Y to Y, we have S base 20 and high voltage base 345 on the high voltage side. So we need to identify the reactance of the transformer in per units. So it's already been given as 12%, which will be 12 divided by 100, then it will be 0.12 per units. So that's the first one, which is the part A, the reactance. The other part, the high voltage side impedance. To find the high voltage side impedance, basically for the base, I would say, Z base, high voltage side, it will be the voltage base in high voltage side square divided by the S base. So the high voltage base, which is 300, let me write it down here, 345 kilovolts squared divided by S base, which is 20 megavolts. Then kilo squared is actually mega, so we can cancel them. Then the remaining 345 squared divided by 20. So the answer will be 5,951.25 ohms. This is Z base for high voltage side. Now let's go to the low voltage side as well. So Z base for low voltage side, this is the second part, part C. This is part B, here's part C. Then it will be V base for low voltage side square divided by S base. We already know this from power system class, but here just like a review. Then V base, it is basically given as 345 without the kilo square. Let me see, pardon me. I think in the high voltage side, this is 345. Yeah, let's see. It's 345 square divided by S base, which is basically 20. Then it will be 59.5125 ohms. Then the last, or let's keep going, which is in D, part D. We need to calculate the reactance, convert to the high voltage side. So the reactance is given as 0.12 per unit. So the reactance in high voltage side, which is the reactance in per unit times Z base high voltage side, then it will be 0.12 times 5,951.25, then it will be 714.15 ohms. Then the other thing, which is the reactance for the low voltage side, which is X per unit times Z base low voltage. Then it will be 0.12 times 59.5125, then the answer will be 7.1415. Okay, then that's it. That's how we calculate all of them. Then we can go here, like here are the solution. So we can see that. Then let's go to the next example. Consider the same example and assume the voltage ratings are 345 Y2 delta. That's the difference. So it's the same value of voltages, but we'll assume it as Y2 delta. So the first question, or the first thing, calculate the turns ratio. So the turns ratio here, which is V line, or I would say like V primary divided by V secondary. V primary divided by V secondary. The primary is delta, is Y, the secondary is delta. So we need to convert this to line to neutral. This remains as is. Line to line, there is no problem in that. So I would say to convert it to line to neutral, it will be V line to line divided by square root of 3. Here, it is the same as V secondary, I would say, which is the same as is, V secondary. Then it will be 345 divided by square root of 3 divided by 34.5. Then after we do this, it will be 5.7735. This is the turns ratio. Again, the turns ratio here, there is a square root of 3. because it is y to delta. So again, in summary, let me do it the summary. Y to y, delta to delta, y to delta, delta to y. So the thing here, when we are talking about y to y, turns ratio will be v line to line divided by root of 3, by v line to line primary secondary divided by square root of 3. Here, the turns ratio will be v line or v primary divided by v secondary as is, while the other one here, it will be v primary divided by square root of 3 divided by v secondary. Then the last one will be v secondary divided by v primary divided by v primary divided by v secondary divided by square root of 3. This yields to be square root of 3 times v primary over v secondary. That's, the summary for the turns ratio. Then the second thing, transformer reactance refer to the low voltage side, and transformer reactance refer to in ohms and in per units. So to find it in ohms, we can say the reactance in low voltage side in per units, it will be the high voltage side divided by n squared, then it will be 740 that we already calculated it before, divided by the turns ratio square 5.7735 square, then it will be 21.42 ohms. Then the next thing is to calculate the transformer reactance referred to in per units. Or before converting this to find it in per unit, we need to find the Z base. So I would say X per units, which will be the value, the high voltage side divided by Z base, the high voltage side. So X high voltage side, which is for 14.15 divided by the per units in the high voltage side. I do believe we already calculated it before, which is 59, or I would say 5,951. 5,951, then the answer will be 0.12 per unit. Okay, then that's it. Here's the solution of the example. Now let's go to the next one, which is the load representation. So the load representation, it is related to the load behavior. So the vast majority of our loads, for example, like the fluorescence, or the light bulb, or for example the motor, we already have all of this in, like, for example, like volts, or on the we have the voltage, but we already have it in watts, sometimes watts and power factor. Now our target is to convert the real power and reactive power to be either impedance formats, or the other impedance format, which is the series and the parallel formats. So all of them, they are the same load, all of them same load. But how about if we need to convert them to be as an impedance in series or impedance in parallel? So again, we used to have the information in the data sheet given as real power and power factor. That's the vast majority. Now, how can we calculate the complex power from that? Then after that, how can we calculate the real power or the R and X? So let's calculate the complex power from the given information. So the real power usually is given in watts. The power factor given as a power factor and lagging as an example. Then how to calculate the complex power? So we can say the complex power itself, which is S angle theta, which is P plus JQ, and it can be as S cosine theta plus JP sine theta, or we can say S times power factor plus J, I'm sorry, S, not P, plus JS sine theta, or in other words, um, S, the angle of 1 minus cosine square of theta, or in other words, S times power factor plus JS angle 1 minus power factor square. So as in summary, we can say P equals S times power factor. Therefore, S will be P divided by power factor. And we can say Q equals S times 1 minus power factor square. Therefore, S will be Q divided by square root of 1 minus power factor square. So it depends on the information, we can calculate the complex power. So if we have the information related to the apparent power, we can say it will be S bar will be S angle cosine inverse of power factor. And it can be positive if it is lagging, negative if it is leading. Or we can say if we have the information about the real power, it will be P divided by the power factor, angle plus minus cosine inverse of power factor. Again, it is positive if lagging, negative if leading power factor. Then, or if we have the information about the apparent power, it will be Q divided by square root of 1 minus power factor square, angle plus minus cosine inverse of power factor. That's, the three possibilities. How can we know if the given value is apparent power? If it is given in volt ampere, this is the apparent power. If it is given in watts, this is the real power. If it is given in var, this is the reactive power. Now, after that, now how can we calculate the R and X, which is the series stuff? I can calculate it here. So assume after, converting, finding S bar, we need to convert it to this format, which is rectangular coordinate, P plus JQ, convert this to P plus JQ, convert this to P plus JQ. This is a must. After calculating the complex power, convert it to this way. Then after that, we will say, as we know, S bar equals V times I conjugate, or V squared as a magnitude divided by Z bar conjugates. Now, when you look at this one, V squared as a magnitude divided by Z bar conjugates, we need to calculate, substitute them. So substitute S as P plus JQ, substitute Z as R S plus Jx, but since it's conjugates, it will be negative. Rs minus Jx. Why? The negative because of the conjugate that we have here. Then, to solve it, we need to calculate R minus Jx. So we can say Rs minus Jx equals to V squared as a magnitude divided by P plus JQ. Now we have a complex number in the denominator, therefore we need to multiply by the conjugate, P minus JQ divided by P minus JQ. So when we multiply by the conjugates, this yields to be V squared divided by, when you multiply by the conjugate, it will be this P squared plus Q squared, and here P minus JQ. So as a result, it will be overall V squared divided by P squared plus Q squared times P. Then the other one minus J V squared times Q divided by P squared plus Q squared. Then you can say this is the RS and this is called XS. Then that's it. This is RS, this is XS. Then the first part, you need to find the complex number. So depending on the load, if we have the real power, reactive power, we have three formulas, this one or this one or this one. The second part, convert this to rectangular coordinates, which is this one. Then the third thing, apply these two formulas to calculate RS and XS. Here, we calculated the load, converted the load from real and reactive power to be as impedance. How about if we need to use the parallel form, which is this one, RP and XP? How can we do it? Using this formula. Those are the formulas associated with the parallel form, RP and XP. Let's look at this example. Given a 100 kilovolt, 7.2 kilovolts, 100 kilovolt ampere, 7.2 kilovolts, or 0.8 power factor, which is a lagging power factor. So we notice that it's given as S. So to calculate the complex power, it will be 100 angle cosine inverse. It's positive because it's lagging. Therefore, make it positive. Cosine inverse of 0.8. So there's no need to multiply by the power factor because this one in kilovolt ampere, this means this is S. And we have the voltage. So we need to find the complex power. To find the complex power, again, this is a kilovolt S. This is angle, cosine inverse, 36, and it's positive because it's lagging power factor. Then S will be 100 angle 36. Convert this to rectangular coordinates. It will be 80 plus J60 kilovolts. This is the first part. The second part, we need to calculate the impedance. To calculate the impedance, you can use Ohm's law, V over I. So let's calculate I first. I, we know V equals, S equals V times I conjugates. So therefore, I will be S divided by V, all of it conjugates. So we can calculate this. Don't forget the conjugates. There's a conjugate here, conjugate here. Conjugate means flip the sign of the angle, so it will be 80 minus J60 divided by 7,200. Here's the angle is 0, so keep it as a constant. There is no, since the angle is 0, it will be 7,200. Then just divide it by this value and convert this to polar core format. That's the currents. Then once we calculate the currents, we can substitute it here to find the impedance. Then we can find the impedance. The second thing, it says, let's change the voltage to be 7.92. Now the voltage now is up. What do you expect the currents? The current will be down, will go down, because for the same amount of power, the current is up. The voltage is up, the current will be down. Then that's it. When we do the calculation, we realize that, for the same S, more high voltage, what will happen to the current will be low. That's how we do the compensation. And there is a decrease. Now the next thing is to here observe, the second part of today's lecture, which is the high voltage overhead transmission line in Jordan. Here we're talking about the transmission line. Again, let's recall, we have transmission line, which is associated with high voltage and extra high voltage. High voltage, which is 132 kilovolts, and extra high voltage, which is 400 kilovolts. However, we have sub-transmission that's associated with medium voltage, and medium voltage can be either 33 kilovolts or 11 kilovolts. Here I'm talking about Jordan, only Jordan. The other thing, distribution, which is low voltage, then which is the 400 volt or 0.4 kilovolts for three phase, or for a single phase, which is 230 volts. Okay, that's the overall thing. Now, today's lecture, we will talk about the transmission, which is high voltage and extra high voltage. Now, let's look at the transmission line, how they look like. The first thing that we have, which is the towers. All of the voltages or high voltages and extra high voltages are based on towers. Then the towers, those are the towers. However, we have this part is called the tubular tower. This tubular tower is very rare. Very rare. And in Jordan, we are using it only on Bayadir area. Only in Jordan, it is used only on Bayadir area, which is close to the eighth circle. Eighth circle. That's the only place where we are using these tubular towers. الدوار الثامن القريب من محطة زين. So there you will see this kind of tubular زين, محطة زين and في محطة البيادر. That's where you find it. However, the remaining are based on this type of towers. Again, these towers can be either high voltage or extra high voltage. So the tubular tower in Jordan is only associated with 132 kilovolts. However, the angle towers or the other type of towers will be either for 400 and 132. That's the first classification. The second classification is associated with the usage. Is it tension or suspension or heavy suspension? What do I mean by tension suspension? Look at this image. In this image, you will see the wire here is like which is called the insulation, the isolators. But you will see the wire is carried here in this part. It will not be cutted. Look at this wire. So it's suspended. The wire is suspended or is being carried by this part. So this is called suspension. The wire is being carried and is not, it's not being disconnected. There is no disconnection. However, look at the tension like this. You will see the wire is being cutted and this part is being cutted. Then we have a jumper in the middle to make this connection. So here we cut the wire. There is a jumper here, a jumper socket here to connect them together. So it's been disconnected. So this part, this is called tension, while the other one is suspension. Suspension, the meaning of suspension in Arabic, تعليق. So أبراج تعليق. The meaning of tension is shed. So by the name or the word suspension, it carries less mechanical force, while the tension can handle higher mechanical force. So where should I use tension? Tension is being used for example, in angle area, when there is an angle, when there is, deviation with 10 degrees, 30 degrees, 90 degrees, when there is an angle on the routes of power lines. Okay. The other thing, we can use it on where like there is mountain or valleys, where there will be high tension, high force, mechanical force, mountains or valleys. Or we can use it every specific group or every number of substation, you will see a tension to add just more mechanical force. So for example, you can see these towers are based on suspension, suspension, suspension. If you are in flat area, then you will see one tension here, then the remaining suspension, suspension, suspension. Just this one is to carry the force. We'll just make sure it can handle the force without any problem. That's the tension and suspension. Now, how about the heavy suspension? The heavy suspension, it's very similar to the suspension, which is basically carrying up the line or the conductor, but you will see like V-shape. It's carrying it like V-shape, and another one is carrying it like here, V-shape. So it looks like both hands carrying the same conductor. That's how which is called heavy suspension. Why we are doing this? What's the point of heavy suspension? Why we are not using suspension, not heavy suspension? Just it's being used for to provide more force, mechanical force. It can handle up to 120 kilonewton. And the main reason for using it, or where we are using it, is we are using it in areas where there is a high wind or where there is, a very large snow. So when there's a high wind, the high wind will make the conductor swing. So we need to have a more mechanical force it can handle more mechanical force. And the other thing, we can use it when where there is snow. So the snow can, for example, when snow starts melting, so it will fall down suddenly, fall down from the conductor, which will make the conductor bounce up and down, which will produce a high mechanical force. Therefore, we need to use a heavy suspension, so the heavy suspension can handle this mechanical force. Okay, now we are done with the heavy suspension. Let's keep going based on the number of circuit carried. So we have single circuit towers and double circuit towers. What do I mean by single circuit and double circuit? Again, I mean, the single circuit, I think they are swapped. The single circuit is denoted by S, denoted by S, while the double circuit is denoted by D. So S single, D from double. So look at this tower. When you look at it, look at here, there is a conductor A, phase B, phase C, and here is another A2, B2, C2. So we can say this is circuit 1 or circuit 2. This is circuit 1. Therefore, this part of towers is double. And by the way, here is earth, and here is earth. So this is double. The vast majority of our power lines are based on double. Why? Because you already purchased a land or own some land, or you're already paying money to establish, I would say like a power line. So if you're making it double, it will be way cheaper us than making it single. Not way cheaper. You're already paying money for establishing a power line, so let's make it double. However, we have some power lines are based on single. So this is a picture for the single power line. This is A, B, C, and here is earth 1, here is earth 2. And the other part, this is a single, also earth 1, earth 2, phase A, phase B, phase C. This is single, and this part of towers, this is earth 1, earth 2, phase A, B, C. This is also single. There's only one circuit. So again, we can donate this one by the letter D, double. This one single by letter S. This single by letter S. This single by letter S. The other thing, when you look at it, you will see two earths. These kind of towers are based on 400 kilovolts. This is based on 400 kilovolts. This is 400 kilovolts, while this one is 132 kilovolts. The vast majority of our power lines are based on 132 kilovolts. So the one is, 132 kilovolts. We will not write anything before the letter S or before the letter, while the 400 kilovolts, because it's 400, we will write the number 4 before the letter S. This is 400 kilovolts, we will write the letter 4, the number 4. Here, write the number 4 before the D. So this is 4D, 4S, 4S. While this one is 132, therefore we will write nothing. Don't write anything because it's 132. So again, in summary, 132, nothing, no number. 400 kilovolts, you will write the letter 4. So we can have like, if 4D means 400 kilovolts, double, and 4S, 432 single, D, me alone, 132 double, S alone, 132 single. Okay? Here is, a picture shows the towers. This is the tower, the ground wires, etc. Phase A, B, C for a single circuit. Again, this is 400 kilovolts, so it will be letter 4, and it's a single, so 4S. And we have two earth 1, earth 2, phase A, B, C. Then it's based on the single circuits. However, on the other picture, you will see earth 1, earth 2, phase 1, 2, 3, circuit 1, phase 1, 2, A, B, C, circuit 2. Therefore, this is double, and this is based on 400 kilovolt tower, so it will be 4D. This is 400 kilovolts. Okay? Then again, this is called 4D, and the other one is called 4S because it's 400 kilovolts. Now, this is another part, it's called the quadruple. Quadruple means 4 circuits. And the symbol of the quadruple, which is the letter Q. Then the quadruple can be like this. Let me do this zoom here. This is earth 1, earth 2, and by the way, this is 132 kilovolts. Look at it. Here, phase A1, phase B1, phase C1. This is phase A2, phase B2, phase C2. Then this is phase A3, phase B3, phase C3. This is phase A4, phase B4, phase C4. So we can say this part is associated with circuit 1, this part with circuit 2, this part with circuit 3, then this part with circuit 4. So as a result, this is called the quadruple, and we will denote this by a letter Q. So if we say 132 kilovolts, if you say 4Q, which will be 400 kilovolts, quadruple. Okay? Now, in summary, before going to the next one, we can have several things, several notations. The first thing, which is S, T, Q. Then we have 4S, 4T, 4Q. The first part associated with 132 kilovolts, while the 4 means 400 kilovolts. Then the first part with S means single circuits. That's T, I would say like DD. Yes. Then this part means double circuits or 2 circuits. Then the last one is the quadruple circuit. So you must distinguish between all of these notations. Now the next thing, let's keep going. The location of the transmission line, which is the starting end and the starting and the ending towers, which is based on the terminal. So the thing here associated with it, the terminal towers at the substation, it's being designed as a special tower. Why? Because we used to have towers here, then here is the substation. So the last tower, again, is called the terminal tower. Then you will see the mechanical forces here different than the mechanical forces here. So which must be designed special. It is a special design that can handle different value, or that can handle, I would say, different forces from the right and from the left. Since it can handle different forces from the right and from the left, then it's a special design. Then we need to make it different. Then we call it a terminal tower. The terminal tower is denoted by T, but keep in mind, we need to make sure, is it double circuit or single circuit? So we can say we have DT, or we have ST, we have QT. Okay? So T means terminal, D double, S single, Q quadruple, or we can have 4DT, 4ST, 4QT. Again, the 4 associated with 400 kilovolts, no number associated with 132 kilovolts. D double, S single, Q quadruple, T is the terminal. Okay? So we are trying to make it more complicated step by step. Okay. Now, let's keep going. The other thing, we call it the angular tower, or in other words, the suspension, the tension towers. The angular towers is basically based on tension. We call it DN. So there is a symbol N here, or SN, or we can say QN. N means the angle. So the angle can be, one of these. So we have 1, which means the angle between 0 degrees to 10 degrees. We have 3 from 10 degrees to 30 degrees. We have 6 from 30 degrees to 60 degrees. Then we have 9, which is 90 degrees. So I would say what I recommend is to write it like this way. I'm sorry. 1 means 10 degrees, 3, 30 degrees, 6, 60 degrees, and 9, 90 degrees. So again, in the angle, for example, this angle is 9 degrees, and this is a single circuit, so it will be S9. This is a double circuit with angle, I would say, maybe 30 degrees. So this can be D3. And it is 132 kilovolts, so there is no other number on it. So again, you can say a tower that can be 4Q3. What does it mean? It means 400 kilovolts, quadruple, with angle 30 degrees. How about if I say S1? This is for 132 kilovolt because there is no number on it. 132 kilovolts, and it is a single with angle 10 degrees. Now, the other classification, suspension tower. We call it L from line. So we have DL, SL, or QL. Or you can say 4DL, 4SL, 4QL if you are talking about 400 kilovolts. Okay? Now, there's another type of towers, which are called special towers. Special towers, we have like junction towers, transposition towers, temporary towers. So transposition towers like this. This is a transposition, shifting the phases. What do I mean by transposition? Let's recall power system class. Phase A, phase B, phase C. Now we swap the phases. So this is B, C, and here is A. This is the transposition. So basically, make A goes this way, B goes up, C goes up. So we are swap the phases. Swap the phases, or in other words, we call them transposition. So how can we swap those? Using this, tower. This is a special purpose tower. And the transposition, we can call it as here is like this 400, 4, and this is a double, D, and we call it TR. TR means transposition. So we denote this, or the notation for it, TR, for transposition. Okay, now how about this part of the towers? This is a suspension. This is a tension, I would say, tension tower. This is 132 kilovolt tower. Now, the first thing, if there is a number 4, it means 400 kilovolts. If there is no number, it means 132 kilovolts. D means double circuits. T means terminal. So like for example, 4DT. And the other thing, if it is S means single, if it is Q will be quadruple, if it is L longitude, if there is N, depending on the, if it's 10 degrees, 20 degrees, 30 degrees, if it's 3, if it is 6, 60 degrees, if it's 9, 90 degrees. And the other thing, there is sometimes we can say +3, +6, +9. This is the additional length. Why do we have the additional length? Basically, any tower has a standard length, as a roughly number like 20 meters. So sometimes you can see the tower on the valleys. If it is in the valleys, you need to increase the length. Maybe you can increase it by 6 meters or 9 meters or 3 meters. They need to add plus something. So the plus something means that there is an additional, and that additional will be added at the bottom of the tower. So here, while the list is the standard. standard that's valid for any DL tower or any DT tower or any I would say DN tower. So it is being fixed. I mean, it's being designed. While if you need to increase the length, add it into I would say, the basement. Line towers, here's this is the line tower or suspension tower. So DL, D from double, L from line, +3, +6, +9 indicates additional heights in meters. For example, when you see DL +3, this means double circuits, or the first thing, 132 kilovolt because there is no number, and it means double circuits, and it means suspension because it's longitude L, suspension, and the last thing, +3 meters extra length. Then the same thing, +6 meters, +9 meters. Okay. Again, the angle towers depending on the angle n, and there is the additional meters depending on 3 means 30 degrees, 66 degrees, 9, 90 degrees, 10, 1, 10 degrees. Transposition towers, again, we can denote it by TR. Before I go to the tower accessories, let's here have a quick recap or quick examples. Assume you have a 4ST+3. What does this mean? The other thing, QL +9. Then other thing, and 4DTR +5. No, I'm sorry. Come on. +6. Then one more, which is 4D3 +9. Or let me say +3. Then the last thing, which is 4S1 +6. What does this mean, each one? This means whenever there is 400 kilovolts, single circuits, terminal tower, and 3 extra length, 3 meters. Extra length. How about the number two? This is 132 kilovolts, quadruple, and it is suspension, 9 meters extra length. How about number 4? This is a 400 kilovolts, transposition, double circuits, transposition or transpose, and 6 meters extra length. Number 4, this is 400 kilovolts, double circuits, and with angle 30 degrees and 3 meters extra length. The last one, 400 kilovolts, single circuits with 10 degrees deviation, and there is a 6 meters extra length. Okay, so you must know all of these notations. It's mandatory that you need to distinguish between all of them. Tower accessories. So the tower accessories can be found in the bottom of the tower. So any tower.
يعطيك العافية دكتور.
عافية.
بس عندي سؤال عن إنه كيف الامتحان بده يكون؟ هو وضع دائرة إيش بالضبط بده يكون؟
ممكن خلي هذا شوي لآخر المحاضرة إذا بعد إذنك.
تمام.
أوكي. لأنه بحب أحكي خارج الريكوردينج، إنه حاليا إحنا في ريكوردينج. أوكي. So is there anybody have any question about this?
دكتور بس عندي سؤال بس على الشيء اللي ورا شوي. دكتور ورا حكينا
which one
انه
here?
في اديشنال حكينا في
link
اديشنال
yes
هايت بنضيفه للتاور اللي هو بيكون زياده، هذا صح؟
صحيح
دكتور في له سبب انه يعني في له اسباب انه بيحطوه زياده مثلا بلس 3 بلس 6 بلس 9 انه في
ممتاز كويس السؤال. تخيل عندنا خط الضغط العالي like this, so there is a tower here and there is a tower here at the valley, and we need to go up here as well. This one must have extra length. Why? Because we don't want the wire to touch the ground. If it's in the standard, the wire can't touch the ground or very close to the ground. So we need to make it extra length. Then we add an extra length here. Add extra length here. So the wire will not be very close to the ground. That's as an example of adding extra length. And the same thing here, depending on where's the highest of the positions. So يعني نوعا ما بيعتمد على التضاريس المنطقة. إذا أنا مرتفعات أو بديش أخلي السلك يمسك الأرض فبدي أرفعه. هاي هي الموضوع. I hope this answers your question.
شكرا دكتور 100%.
العفو. Is there any other question about the notation? Okay, just give me a moment. Okay. Now, for the tower accessories, every tower, there must have some decoration, not decoration, I would say like accessories to make sure everything is fine based on the standard. One of the accessories, there must be anti-clamping wires. Sheik مانع تسلق or anti-clamping wires. So this for protection to avoid the people and to avoid the animals from climbing the power lines. So here it will be very difficult to climb the tower because of the anti-climb, I would say wires. The other thing, there must be a danger plates. It will tell the people, danger, please do not come close to it. And there should be a tower number plates. The tower number will say, for example, this is tower number 1 or 2 or 3, and will give an information. This tower is belongs to the, for example, like Al Bayadir, South Amman, or for example, belongs to Airbid substation, whatever, like depending on the power line. So there should be a circuit number with it, circuit colors and phase colors, so we can know the sequence, if it is positive sequence, negative sequence, and the phase color, this is as an ID for the circuits, for the I would say the power lines. Each power line has its own color. So for example, red, white, red, it's only associated with tower, or I would say not tower, circuits that connecting the circuit number 1 between, for example, South Amman and Al Bayadir. This is mandatory. There is no other circuit sharing the same color code, so that's why we call it ID. And the circuit number, it will say like circuit number 1, circuit number 2 for the power lines. Here's again like how the terminal tower looks like and how it can handle the mechanical forces. This is also how the D1 with 10 degrees. Again, keep in mind, this is a double circuit and this is based on 132 kilovolts. There's only one earth, and here there is only one earth, 132 kilovolts. Now, the other thing which is related to the insulator. So the insulator, what do I mean by insulator? Let me go to the beginning of the high voltage, which is here. Where is it? Sorry, yeah. When we talked about the tension and suspension, you will see there is an insulation, awazil, insulation. So this insulation, it's being used for two purposes. The first purpose for that is to carry the wire. The second purpose is for electrical insulation, to insulate the wire from the tower body, because the tower is made from steel, then it will conduct electricity. So we need this to insulate, to provide an electrical insulation. Therefore, the insulation has two jobs. The first job is basically electrical function, to insulate, complete insulation between the electrical wires or the conductors and the towers, and the mechanical, to carry the wires. Okay? And they can be in different things. It can be as a rubber, or it can be as a glass or porcelain. So rubber, or sometimes we call it polymer. Polymer or rubber, both of them the same. So if you have the glass, the rubber, or the polymer, that's the specifications for that. So the polymer or the rubber, less weight. The glass and porcelain have heavier. But the thing about the glass and porcelain, they have longer life cycle. But the rubber, lower life cycle. But there is a drawback for the glass and porcelain, whereas there will be the dust and the humidity. Dust and the humidity impact those. So to remove the dust and the humidity, especially during the summer, we need to do something we call washing insulators. We need to wash these insulators during the summer. However, for the rubber, it will not impact it. It will not be impacted by dust or humidity. So therefore, there is no washing. So I would say, the rubber is good because it's lighter, less weight, no washing, cheaper, but the problem is its lower lifetime, lower life cycle. However, the porcelain and the glass, they are heavier. That's the drawback, but they need to wash them. But the thing about it, which is it can take dust and humidity, therefore we need to wash the insulation material. That's here are some specifications about the leakage path for each one, if it is polluted or non-polluted, depending on if we are in the areas, everyone. And there is the mechanical strength, if it is tension 160, suspension 80, heavy suspension 120, and the durability, insulators do not age significantly in porcelain and the glass. However, the porcelain, the problem of it, it can crack. Difficult to detect the crack by visual the crack. It can crack because of there is a leakage path, and again requires washing during the summer. While the glass, the drawback of the glass, it's made from Pyrex glass. It can rubber. If it is broken, it will be broken completely broken. While the porcelain, it can be broken partially. So porcelain, I would say, is kind of, safer than the glass because it will be broken partially, while the glass will be broken completely. But the thing about it, a glass is used in deserts, where in high polluted area. which make it better than the porcelain in high polluted area, while in the suburbs or when there is no desert, then use the porcelain. Or you can use the rubber, which is, or the polymer or the rubber, which is basically, I mean, or the prices, the drawback is high and the lifetime is low. That's the disadvantages. Now here are some faults, break-in, or some major things, which is basically if there is dust or a lot of dust and humidity, then the humidity, like water and the dust, will make a leakage path. So the current will keep flowing from high voltage toward the tower. Then it will cause a breakdown. So this one will be broken, especially in pollution area, high pollution area. So there will be something we call it high leakage currents that cause damages and can cause flashover, like we see here, like flash. Okay. Now the conductors. So let's stop here. Next lecture we will talk about the conductors. Okay. Any question? Okay, I'm gonna stop the recording. Then let me talk a little bit. Okay. Now I